Hi, I'm Chris, a professional physics tutor. By the end of this video, I'm going to teach you how to do problems like this. We have a mass held at an angle of 40 degrees on a string of length 8 meters. After releasing it from rest, how fast is it moving at its lowest point? So let's jump in. Before we do this problem, we got to talk about the concepts needed to solve it. Because solving physics problems is never just about the problem, it's about how you solve the problem. And if you know the process, you can solve many different problems, not just this one. All right, so this problem involves a concept called energy. So what is energy? Energy, broadly speaking, is the capacity to do work. It is what allows your computer to run, your phone, your dishwasher, your stove, your refrigerator. Anything that does anything requires energy to work. Your own body. You consume food, and the food contains chemical energy that gives your muscles, your brain, and all the systems in your body the nutrition it needs, the energy it needs to do what it does. So oftentimes I think of energy as like a bar. There's an amount of it, and when there's enough of it, things can work. And when there is not enough, things stop working. So for example, we have a little robot friend right here. This robot on the left is full of energy. They're excited. Their lights are on. They're standing up, maybe dancing. It's a good time. And then on the right, we have a robot with low energy. They're slumping over. The lights are off. They need a recharge. That's basically what energy is. So that kind of energy is really about complex systems, devices, living beings. But individual rigid objects can have energy too. There are a couple types of energy objects like this can have. One is kinetic energy, the energy of motion. The more massive something is and the faster it's moving, the more energy it has. And there's an equation for this. The kinetic energy of an object is equal to half its mass times its velocity squared. So the faster an object is moving, the more energy it has. And the kinetic energy does not depend on the direction the object's moving, only the absolute value of its speed. The other type of energy an object can have is potential energy, which is energy stored in force fields. For example, I've drawn a mass sitting on the edge of a table, and of course, gravity is pointing straight down. This mass, if it is knocked off the table, will pick up speed as it falls. That speed, the energy of that speed, comes from energy stored in gravity because it's up high on the table. The equation for potential energy due to gravity is the object's mass times g times its height. And this is not absolute potential energy, it's relative to a reference height that we choose. Usually it's the lowest point. So we say the lowest point has 0 potential energy. But if you choose a different height to be 0, that works too. Okay, bringing it together, energy is conserved. So I like to think of potential energy and kinetic energy like two buckets that pour energy between each other. As an object rises, it converts kinetic energy to potential energy, slowing down and increasing in height. And as an object falls, it converts that height back into speed, converting potential energy to kinetic energy. So these two buckets can interchange energy between each other. And this process of converting potential energy to kinetic energy and vice versa is called work. Specifically, conservative work. Conservative meaning the force field conserves energy. Now, of course, an object doesn't always keep the same amount of energy for itself. It sometimes takes energy from its surroundings or gives energy back to its surrounding. And that is called non-conservative work. So drawing the arrow here, work, non-conservative. So energy itself is never created or destroyed. It's only converted between forms and between objects. And when it's converted, we call that work. When it's converted between forms, we call it conservative work. And when it's converted between objects, we call it non-conservative work. And there's an equation for this. I'm actually going to write two equations, but they're technically the same equation. So for these equations, if we have an object, we can take a snapshot moment in time, before and after. And in one equation, the left side is the before snapshot. Potential energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final. And here we're talking about when the only force that does work is a conservative force like gravity. Any other force would be at a 90-degree angle and contribute no work. Now, we're not talking about how forces contribute or take away work from an object in this video, because we're sticking to what's necessary for the original problem that we're building toward. The second equation is what happens if we get the kinetic energy on one side and the potential energy on the other side. So that says the change in an object's kinetic energy is equal to negative the change in an object's potential energy. And this makes sense, right? Because if an object is converting its kinetic energy to potential energy, then whatever kinetic energy it loses, it gains in potential energy. And whatever potential energy it loses, it gains back in kinetic energy. So let's look at a simple example before we do our initial problem. We've got a box sliding down a frictionless slope from a starting height of 8 meters. Starting from rest, how fast is it moving when it reaches the bottom? So to start out, we want to write down all the values that the problem gives us. It gives us a starting height of 8 meters. It tells us it's starting from rest. What that means is its initial velocity is equal to 0. Now, we don't know what the mass is, so we'll write that as a question mark for now. But when doing physics problems, it's important to have faith that the problem does tell you enough information to solve the problem. Okay, so how can we analyze this? We've got a mass, we've got a height, it's sliding down, and this slope, as you can see, is kind of bumpy. And so if we wanted to do it using forces or kinematics with acceleration and velocity, it'd be really hard to do. And we're not given any angles or any of that information. We're only told the height. Now, here's the important thing to know. When you're looking at a problem and you see keywords height and how fast or what is its speed, and these are like the major ideas of the problem, this should immediately trigger your brain to be like, conservation of energy. That's what we're doing here. So, what's our equation for conservation of energy? We have a couple. We have kinetic energy equals 1/2 mass times velocity squared. We got potential energy equals mass times g times height. And we have conservation of energy. So the reason we can use conservation of energy is even though we have a normal force here, the normal force is pushing away perpendicular from the ground, it's always pointing in the perpendicular direction to the motion. So the normal force will never contribute any work. It will never contribute to the conversion of energy. So we can use the conservation of energy equation. So potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Okay, now that we've written down this equation, the conservation equation, it's time to start putting in expressions. We've got expressions for potential and kinetic energy here. So below this, we will now put those in. What's the initial potential energy? Well, we don't know a lot of numbers. We know some numbers, but let's not put in the numbers yet. Let's just put in the expressions with variables. So the initial potential energy, that's when it's up here at the top. So that would be mass times g times height. And again, you think, well, how can we write this? We don't know what the mass is. That's the thing about physics problems, is you can still write the equations if you don't know what the variables are. So we're going to write the equations and trust that the problem has given us enough information to solve it. So then, what is the initial kinetic energy? Well, it starts from rest, which means the initial velocity is 0, which means we add 0. mgh plus 0 is equal to, then its potential energy final, that's when it's down here, final, and well, it's at the bottom of the slope. So the height is going to be 0. So mass times g times 0 is 0. Plus its final kinetic energy. And again, we don't know what the mass is, but we just write in the expression. 1/2 mass times velocity squared. All right, so we can simplify this. mgh equals 1/2 mv squared. And if you look at this, this also is correct with the change in the change in potential energy, because it loses mgh of potential energy, is equal to the change in kinetic energy, because it starts from 0 and ends with 1/2 mv squared. So that just goes to show that these two versions of this equation will tell you exactly the same thing. All right, so now that we're here, we see something significant. The problem didn't tell us the mass, however, it's on both sides. See here and here? So if we divide both sides by the mass cancels out. And we just have gh equals 1/2 v squared. Okay, and a couple more steps of algebra gives us velocity is equal to square root 2gh. Now, I'm going to tell you something very important, so listen closely. Do not memorize this. Do not memorize v equals square root 2gh, because it is only true in certain special cases. What you want to remember is this whole process. How to start from kinetic energy, potential energy, set up the equations, do the algebra, and figure out an expression for the specific problem you're looking at. This part will be applicable in many, many problems. This equation down here, only applicable for a small number of problems. And if you memorize it, that's a waste of brain power. That's a waste of effort. So don't memorize v equals square root 2gh. So now that we have v equals square root 2gh, we can plug in some numbers. 2 times 9.8 times 8, take the square root, and we get 12.5. 12.5 meters per second. And in the future, maybe I will be more rigorous about the number of significant figures I include in the problem, but this is just a simple example, so I'm not going to worry too much about that. All right, back to our original problem. We've got a mass hanging by a string at an angle of 40 degrees, and it swings down to its lowest point, and we want to know how fast it's moving here at the lowest point. It's got some speed, and then it's going to swing back up the other side. So what we do here is we start by thinking, all right, we've got a difference in height. We're asking for speed, and it's released from rest. So, we want to use conservation of energy. So for this one, it turns out we can use a lot of, oh my goodness, we can use a lot of the reasoning we already have. So if we write down the kinetic energy, potential energy expressions, and we write down the conservation of energy equation, substitute the expressions, do the algebra, we end up with the same V equals square root 2gh. Now, I guess it's a little ironic that I told you not to memorize this, but it is also applicable in this problem as well. So we've got an expression, velocity equals 2gh. Now the question is, what is h? So we want an expression h is equal to some number, ideally. So before we go on any farther, let's just write down the information the problem gives us. It gives us an angle of 40 degrees. It gives us the string length of 0.8 meters. And again, it does not give us the mass. So given this information, we better be able to find h. So your first thought might be, h is height, right? They give us a height. The height they give us is the length of the string. So h equals 0.8 meters, right? Well, that is not correct, because remember, height in potential energy means the change in the height of the object, which means that the height is what we get if we take the difference between the height of the object at the beginning and the height of the object at the end. So the height is, in fact, this portion. H is down here. L is the whole thing, but H is just the portion of the string that is below the initial height of the object. So, how can we find this height? Now it's time to put our brains to use and do some geometry. We've got ourselves a triangle here, and specifically, we have a right triangle right here with this dotted line. Now, how is this going to help us? H is outside the triangle. Well, we know that H is going to be L minus the portion of the string that is inside the triangle. So we can call that X. So we know H equals L minus X. Well, now we have to find out what X is. X is the adjacent side of the triangle, and L, in addition to being the vertical distance of the string, is also the full distance of the string as the hypotenuse of the triangle. You remember SOHCAHTOA, sine, cosine, and tangent? Well, the cosine of the angle, and I'm just putting theta here, not 40 degrees, because it's good practice to use symbols while doing a problem, and then plug in the numbers at the end. The cosine of the angle is equal to the adjacent side, which is x, divided by the length of the string. And we're looking at this length right here, the hypotenuse of the triangle. So if we solve for x, we get x is equal to L times cosine of theta. All right, now that we have an expression for x, we can substitute it up back here, and we get h is equal to L minus L cosine theta. And we can even simplify that by factoring out the L. H is equal to L times 1 minus cosine theta. Okay, now it's time to bring everything together. We've got V equals square root of 2gh, and we've got h equals L times 1 minus cosine theta. So that gives us the final expression. Velocity in the final snapshot is equal to square root of 2 times g times L times 1 minus cosine theta. And now we have all these variables that we know all in a row. So now it's time to plug in the numbers. V equals square root 2 times 9.8. I'm going to leave the units off for now because in these moments, the units can get a little cumbersome, especially when drawing with the mouse. Times 0.8 meters times 1 minus cosine 45 degrees. Running out of space. All right, there we go. So now we calculate. And remember, when you calculate cosine of 45 degrees, you have to have your calculator or your calculating app in degree mode, not radian mode. And the answer I get is our velocity at the lowest point is equal to 2.14 meters per second. Again, don't memorize this part. Don't memorize this expression, because this expression is only valid for this specific problem. When you use other problems, you have to go through the conservation of energy. You have to do the geometry yourself. This is the important part. The important part is the geometry, the conservation of energy, and applying that to the problem. If you do that, you will be able to solve dozens of conservation of energy problems. Not just a mass on a string, not just a box sliding down a slope, but many different types of problems that you have never seen before. Okay, to recap, energy is the capacity to do work. If you have a lot of energy, you can be active. If you have not much energy, you can't do much. Individual objects can have energy. Objects in motion have kinetic energy. Objects in force fields, like gravity, have potential energy. When moving in conservative force fields like gravity, energy is conserved. That means you can think of energy like two buckets that can pour energy between each other and can pour it out and can receive energy from outside. When you see the keywords height and speed in a problem, that should be a suggestion to your mind that you want to use conservation of energy. You solve these problems by writing down the information the problem gives you, identifying what you're looking for, then writing down the relevant expressions, like kinetic energy is 1/2 mv squared and potential energy is mgh. You write down the equation of the major concept, in this case, conservation of energy. Then you substitute in the expressions, do algebra on it to eliminate unwanted variables, come up with an expression with the variable you're looking for, and then calculate. Finally, depending on the situation, there may be extra steps. You may have to do geometry. You may have to bring in concepts from other chapters. And most importantly, do not memorize the final expression. Remember the process of deriving it from the beginning. That's it for this lesson. If you would like personalized tutoring lessons, visit my website in the description where you can find out more about my business and sign up. If you have questions or comments on this specific video, you can let me know down below. Don't forget to like and share and all that to help this channel grow. And feel free to subscribe if you want to see more lessons like this and studying tips in general. Thanks for watching. Peace out.